Okay, guys. Happy Friday. Seminar today at 1 o'clock. Please don't forget that. Usual room over there. Extra credit applying to test 1. Lab this afternoon. We said the answer sheet for the sulfanilamide lab was due Monday. I realize that there's a question on the literature part that we're not going to have covered by then, the one about the sort of directing effects. We're going to have to postpone that till probably, actually I'm not sure. Let's talk about it on Monday. That answer sheet's not due on Monday. Maybe next week in lab or next Friday, we'll see. There's something we haven't covered yet. Any questions about the introductory mechanism? The EAS mechanism, electrophilic aromatic substitution. Any questions about it? You need to know how to draw your resonance structures for your cation. Okay? You do get a resonance stabilized cation. From there, something removes the H to restore the aromaticity. Questions about that? There.
How do you know where, when there's substitution, how do you know where it's going to add?
Well, if it's just benzene, anywhere.
But if there's substituents?
We'll talk about that because you'll have substituent effects. Okay. So what we're going to do is we're going to look at different types of electrophiles. And the first type is going to be halogen. Halogenate benzene ring. It will react with bromine, but it typically requires a catalyst, a Lewis acid catalyst. In each case, we have to sort of generate the electrophile. Here we have bromine. We can show bromine like this. Of course, there's lone pairs all the way around. If we had an alkene, cyclohexene, react with bromine in organic 1, these electrons would just react with bromine, right? We just did that. And we would get, maybe bromine here plus Br minus. And then we could maybe show cation here, but what did this do immediately? Back bonded. And we got the bromonium ion. Okay? Benzene doesn't react with bromine as readily as a regular alkene because the electrons are involved in aromaticity. We need to activate the bromine somehow. We can activate it with the Lewis acid. These electrons bond to the iron. Lewis acid, what's the definition of a Lewis acid? Accepts an electron pair, right? Okay, that's what it's doing. Iron, all your metals have empty d orbitals. And that's what's accepting the electrons. This gives bromine, Fe, Br3. And this bromine is now positive, and the iron is now minus. Complexation with the Lewis acid. Now, this is electrophilic enough for the benzene ring to attack. I'll redraw the benzene ring. This is essentially your E+. But we're attacking here. That's plus, but this is electrophilic. We attack here, and this bromine leaves. Why is this bromine a better leaving group now? Because now it has a positive charge. How do you make oxygen a better leaving group? You protonate and give it a positive charge. Bromine has a positive charge. Now the electrons will attack here, kick that off. What does that give? Okay, there is an H here. I'm going to draw it in. I'm going to draw it in here. And this is a carbocation. Plus what? I could draw this out with the bond, or I could just draw it as FeBr4 minus. But all four of those bromines are covalently bound to the iron. It's a minus. So, what did we call this on the previous page? On the previous page, it had E here instead of a bromine. What do we call it? Sigma complex? Yeah. It just looked just like on the previous page, except it had an E instead of a bromine. I mean, there it is. It's just E instead of bromine. So here's our intermediate. It's not aromatic because it no longer has a p orbital here, but it is resonance stabilized. Okay, we can draw resonance structures. I'm not going to draw them all. It's the same as on the previous page. Electrons here, electrons there. Resonance stabilized carbocation intermediate. What do we have to do to get final product? To get this? Something has to remove the H, and you restore the aromaticity. I should have drawn this out. Let's draw this out, Br3 with a Br. At this point, well, first of all, what's the byproduct up here? The byproduct is HBr. At this point, the iron is like, hey bromine, I like you, but I don't want to be minus. You and your electrons need to take a hike. The two electrons take a hike, and they go and bond to the H. These electrons move down here, and what does that give? It gives those two products, plus what? What do we have here now? We have FeBr3 reform. Something takes the H, you restore the aromaticity, you now have a bromine there. When we do chlorine, we'll see that we can use like FeCl3 or aluminum trichloride, very common with chlorine. Note that you can also just use iron. Because iron will react with bromine to give, guess what? FeBr3. If you want to balance that, you're welcome to do it. So a lot of times, especially in the old days, they would just throw in a little iron, like a rusty nail or something. Or maybe not a rusty nail. And you get a little bit of the bromine reacting with the iron, making a little bit of FeBr3, and all you need is a little bit of catalyst, and then the catalyst is formed. Questions about this mechanism? Same mechanism works with chlorine. Cl2. Typically when you use chlorine, you don't want to mix your halogens, so you would use like FeCl3. Or aluminum Cl3, which is most common with chlorine. AlCl3 is very common. Otherwise identical for fluorination. Fluorination, well, very hard to do because it's so exothermic. We won't cover fluorination. Your book may not even mention fluorination. There are ways to do it. It's typically very difficult. Iodination, on the other hand, is a little bit difficult. It's not really difficult, but it suffers from being not reactive enough. Fluorine too reactive, iodine not reactive enough. Because of that, you can't just use a Lewis acid. You actually have to use an oxidant, and you actually have to produce I+. In the previous mechanism, did we produce Br+? Well, you might say we had a Br+ there, but it was complex. And we certainly did not attack the Br+. The Br+ was the leaving group. Here you actually have to make I+. That would come from iodine and an oxidant giving I+. Your common oxidants are like copper 2 chloride. What's that? Cupric or cupus? Is this thing on? Cuprous or cupric? I thought it was an easy question. Hydrogen peroxide, HiO4. In addition to HiO4, you can also use the salt, like sodium periodate, potassium, some types of oxidant. For example, here, iodine, cupric chloride, you can get the iodo. What does this make? We're not going to do mechanism, but what does this make? It forms I+. Now you just do the same mechanism we did on the front page, except on the front, this was what? E+. But this generates I+. Same mechanism. Those that did iodination in the lab, what did you use to iodinate sulfanilamide? Who did iodination? Selma, what did you use for iodination? Sam? Potassium iodate? Yeah. KiO3, right? And what else did you use? Sodium iodide? Yeah. Iodide and an oxidant. There's actually two oxidations. You first went from I- to I2, and then you went to I+. That's two oxidations. Or you could have just started with iodine. Somebody started with iodine. Started with iodine, but you still used an oxidant, right? The iodine was oxidized to I+. Yeah. Okay, actually the fluorine was down there. Use of fluorine, well, you better stand back because it tends to be explosive. Why? Because the FF bond is so weak and the CF bond is so strong. There are alternatives. Today you can get these what are called NF reagents where the nitrogen has a positive. So something that can attack the F and the positive nitrogen can leave. These are nice stable solids. A lot of my students have used these in the research lab. We'll also see the Diazonium reaction is a classical alternative to making fluorocompounds. We'll cover Diazonium chemistry in a week or two. So that's halogenation. Next, let's look at nitration, which we did in lab Wednesday and we're doing today. Nitro group is very common with aromatic rings. Not so common with just saturated systems. Usually you see it on an aromatic ring. Benzene ring, nitric acid, and an H+ catalyst. You can make nitrobenzene. Nitrobenzene is like one of the main components in old-fashioned shoe polish. If you remember that smell, nitrobenzene. You need to know the Lewis structure for the nitro group. It's here, dipolar, net neutral. Here's the E+, is the nitronium ion, NO2+, and here's the Lewis structure for that. How do we form this? Let's start with the Lewis structure for nitric acid. So there's nitric acid. What do we have to lose to get to the nitronium ion? Rachel? Have to lose the H. We're going to lose the O also. We're going to lose the OH. How do you make OH a better leaving group? What's the purpose of the acid catalyst? There you go. These electrons protonate. What does that give? It gives this. Now, we can just show this leaving. If that leaves, what do we get? Which is actually 2+. It's actually not a good resonance structure at all. We lose water. Can we draw a resonance structure of this? One that will be much better. What about moving these electrons in? What does that give? It gives you a nitronium ion. So this is just a lousy resonance structure of the nitronium ion. This is better because there's only one positive as opposed to two positive and a negative. So basically you protonate nitric acid and it loses water. That gives the nitronium ion. Now you can do your mechanism. So I don't erase this, I'm going to kind of come here. I'm going to draw the benzene ring here. We attack the central nitrogen because the ring is bonded to the central nitrogen. I'm going to pull away from the bottom and attack here. But the nitrogen already has 8 electrons around it, something has to leave. So as I attack, I'm going to move electrons onto one of the oxygens. Your choice. What is that electron movement here? First off, there is an H there, right? There's an H on every carbon. But now there's a bonded to the end. The end is double bonded to one O still. And then the other O is single bond, right? And how many lone pairs over here? 3, because right here, third one is moving over. This is minus, and that's plus. There's your nitro group, okay? We still have pi bond here and here. What's here? Positive charge. So here the benzene ring attacks the nitronium to make the sigma complex. What do we need to do next to get final product? Something takes the H. What could take the H? Water always works when you're under acidic conditions. For me, I like to use the minus that's here. What acid catalyst did we use? This is going to be a strong acid, like sulfuric, etc. And so at this point, we have an HSO4 minus floating around. H plus, HSO4 minus. This, I'm not going to show lone pairs here, but this could take the H. These electrons can move in, restore the aromaticity, and we get final product plus H2SO4 reformed. I like to form the actual acid. But of course, how does H2SO4 exist? It really exists H3O plus, HSO4 minus, okay? Mark?
Can the O minus back bonds
Where?
in all the way to the right?
Here?
Yeah.
Back bond where?
To the plus.
Here? Not a bad suggestion.
Close.
I mean, it's theoretically possible. Why do you want to do that?
I mean, can it just happen? Like because it's closer?
Certainly theoretically possible, but in terms of the mechanism, yes, it's certainly possible. But this is your typical mechanism. By the way, that could have been asked back over here. We go back to the bromination. Did we have this species formed in the bromination? What about this? Could this back bond? It certainly does when you do an alkene bromination. This doesn't back bond because it doesn't need to. Why does it not need to? Because this is resonance stabilized. And so because this is resonance stabilized, you typically don't get that back bonding, you don't get bromonium ions like you do when you just brominate an alkene. So while theoretically it could, it's never really shown. I don't know if it's been proved that it doesn't do that. Okay, so there's your nitration. Now in lab, we did not use sulfuric acid. Use sulfuric acid, it's typically going to be a fast nitration. Sometimes you don't have to use an acid. Sometimes you can use acetic acid, whether or not it's strong enough to really be the acid catalyst or not sure. But here's something wild and wicked. Nitric acid can actually protonate itself. Okay? I mean, here's one nitric acid. You could have another nitric acid that's ionized, what would that be? HNO3 minus. I mean, nitric acid can supply a proton. So you could have one nitric acid protonating another. So using sulfuric is sort of just textbook. There are other ways to get your protonated here. And you get the nitronium ion. That's your electrophile. Okay. Once we make nitro is very versatile. It's your typical precursor to an amino. While there is fancy chemistry to put an amino directly on a ring, it's usually never done. Instead, to get to amino, most commonly you first nitrate the ring, then you reduce the nitro to the amino. That is a reduction. We're removing oxygens, we're adding H's. This is done two different ways. One way is to use an active metal. Iron, tin, or zinc is three common ones. You can use others. Indium. With an acid catalyst. And it's probably not really a catalyst, it's probably consumed. But with H+. This is called a dissolving metal reduction. You start with a metal that's not going to dissolve in anything. As it reacts, for example, the iron becomes, what acid do you want to use here, everybody?
H2SO4.
Okay, H2SO4. You can also use maybe HCl. The iron is going to become like iron sulfate, and now it's going to dissolve. This is typically an aqueous acid. Here the iron is iron metal, so the oxidation state is 0. What's the oxidation state of the iron here? +2. So what has happened to the iron? The iron has been oxidized. That means something has been reduced. What's been reduced? The nitro group has been reduced. Now, just to show you, iron, these metals do react with acid to give this plus hydrogen. And these are your kind of your active metals. This doesn't mean that this produces hydrogen when you reduce this, but this is just something to be aware of. That being said, another way to do this conversion is with hydrogen gas and a palladium or nickel catalyst, just like you reduce alkenes and alkynes. That same process will reduce the nitro to the amino. We're not going to look at a mechanism or anything, but hydrogenation will do this also. In lab, we will do a dissolving metal reduction next week, and you have a choice of using either, can't remember, it's either iron or zinc. At one point I had tin in there, but I took it out. I think right now it's listed as either iron or zinc. Your choice. There's different acids that can be used. ACl. You can even use ammonium chloride. Some type of proton source. Okay. Next reaction is going to be to put on a sulfonic acid, SO3H, with a Lewis structure like this. This is done using sulfur trioxide and sulfuric acid. Let's start with a Lewis structure for sulfur trioxide. Let's see. One, two, three, four. 1, 2, 3, 4, 5. All depends on if you want to expand the octet 2, 4, 6, 8. It's already expanded. Let's see how this looks. Is that a reasonable Lewis structure for SO3? I mean, it's got 10 electrons around it. If you only want 8 around it, you would have to have 2, 4, 6, 8. Minus, minus, and this be 2 plus. I mean, these are resonance structures. But we know sulfur, because it's a row down, has d orbitals and it can expand its octet. So to get there, you would just move these in, and we could show this. I think this is sort of a typical, well, the most common resonance structure there. The benzene ring doesn't react with this that readily. It requires a sulfuric acid catalyst. What do you want to do first? Want to make use of that catalyst. What do you want to do? Protonate something. Well, we can protonate this here. You see, this is positive, and we're going to attack this sulfur. That's how the ring gets this bonded to sulfur. You see, there's a lot of donation here. This minus is pumping electrons into the sulfur. Apparently, it decreases the electrophilicity of this sulfur enough that the benzene won't attack it. How can we keep this from pumping in as much? Make it neutral. If we make this neutral, two things. Now this oxygen doesn't pump in as much because it's no longer minus. Also, now our molecule here has a positive charge, where over here it was net neutral. So this is just a more reactive species with that proton on it. Now the benzene ring will attack the sulfur. And this is our E+. We can attack here. Now, because sulfur can expand its octet, you don't have to really move anything. You could, you're just going to get a little resonance structure of this. But if you don't move anything, what do you get? There's an H there. Benzene ring is now bonded to the sulfur. There's 2 double bonds to O and an OH. Yeah? We just made that bond. But there's your sulfonic acid. And there's your sigma complex, resonance stabilized cation. What do you need to do to get the final product? Something needs to remove the H, restore the aromaticity. What do you want to remove the H? How about this guy here? Take the H, electrons move in. We get this, and we reproduce our catalyst. Sort of a miscellaneous comment here. This may not be in your textbook, but it's something that we can discuss. Sulfonation is actually very reversible. That is, you can take the benzene sulfonic acid, heat it in acid, you can get benzene back plus SO3. You can reverse it. And it would be a good exercise for you to sort of do this mechanism for the reversal. Now in the reversal, what is the electrophile? The E+. It's H+, because what are we adding in place of this? We need to get an H on there. H+ is what? The ring attacks H+. But then, to restore the aromaticity, when it attacks H+, you get what I just erased up there. You get the sigma complex that's just up there. But from that point, instead of removing the H and going to this, somehow you remove the SO3. And so it would be a good exercise to look at how that could go. It's a very reversible reaction just by doing this. And later on, we may revisit this and talk about protecting groups. Let's see. I could have referred to this earlier. This is just a drug that has an amino group in it. How do you typically put amino groups on a benzene ring? First nitrate and then reduce. This is actually an interesting compound. Well, I believe without the amino group, I'm pretty sure, you have to read it. Does it say, is that thalidomide? Does it say that's thalidomide?
Yes.
Yeah. Without the amino group, that's a drug that used to be given to pregnant women to treat morning sickness and nausea. Fortunately, it led to birth defects. And the drug was pulled from the market, discontinued, etc. But here they found by adding an amino group to thalidomide, it's useful to treat myeloma. And so now it's a new drug again. Okay. How does the mechanism look? Let's recap. What did we put on the ring? We showed you how to put a halogen on the ring. What else did we put on the ring? Nitro, so that's a nitrogen on the ring. The amino comes from the nitro. Sulfur on the ring in the form of a sulfonic acid. What else would you like to put on the ring? What about an oxygen? Oxygen is not easy to put directly on. Again, diazonium chemistry will put oxygen on. What other type of atom or group would you like to put on the ring? Well, oxygen would be like an alcohol.
Cyanide.
What?
Cyanide.
Cyanide? Okay, that'll come from diazonium chemistry. Diazonium chemistry is very versatile. But what's the atom you're putting on when you put on cyanide on? Carbon. What's another type of carbon group to put on the ring? Methyl? How about an alkyl? Methyl, propyl, butyl? Yes, we can do that. Ketones? Yes. Your carbon groups are going to be put on by chemistry called Friedel-Crafts. Friedel-Crafts alkylation or acylation. But before we do Friedel-Crafts, we need to take a sort of a sidebar here, and we need to discuss substituent effects. Substituent effects are basically, what if you have something like nitrobenzene and you react it with bromine and a rusty nail? What is this going to put on the ring? It's going to put a bromine on the ring. But where? Because if you have one group, that position, that position, that position are not the same. Where's the bromine going to go? It's actually going to go meta. But why? Basically, what is the effect of this substituent on the reaction? That's a substituent effect. Yes, it will go meta. And I could also ask you this question. Does nitrobenzene react faster with these conditions or slower? It actually reacts much slower. It's going to be a more difficult reaction than if that was not there. Again, that's a substituent effect. And the faster, slower is the first thing we're going to look at. Activation or deactivation? Does this group activate this reaction or does it deactivate it?
Deactivate.
It deactivates it. So let's introduce this. Basically, if you have an electron donating group net on your ring, it's going to be more reactive than benzene. A net donating group. If you have a net electron withdrawing group, it's going to be less reactive than benzene. But why? Your electron donating groups lower the transition state energy for an EAS reaction by stabilizing the carbocation intermediate. While on the other hand, electron withdrawing groups destabilize. This is illustrated down here. Let's just look at benzene in the middle, and then we'll compare. You have some type of transition state leading to the sigma complex. Okay? Over here. If this is a donating group, is the donating group going to stabilize this carbocation or destabilize it? Donating groups stabilize positive charges. Okay? Because it stabilizes it, it's going to make the transition state energy lower. It makes the carbocation lower. I mean, they didn't show it much lower, but it's lower, right? Because you have a more stable intermediate, it's going to be a faster reaction. On the other hand, if you got a withdrawing group on the ring, do withdrawing groups stabilize carbocations? No. So it's going to make this higher in energy, and thus the transition state leading to it higher. That's going to be a more difficult reaction. Here you have to go over a mountain. Here you have to go over a little molehill. But this is what we got to know. Of the various groups, how do they behave? Which groups are donators? Which groups are withdrawers? Now, I divide my groups up into groups 1 through 4. The book maybe does it a little bit differently. My group 1 is going to be strong activators or donators. These are going to be atoms with a lone pair other than halogen. For example, oxygen, nitrogen, etc. As long as the nitrogen has a lone pair. These are going to be strong activators. For example, right here, there's an example of group 1. That's an atom with a lone pair, it's not a halogen. Strong activator. Why is that an activator? First off, electronegativity. Which is more electronegative, carbon or oxygen? Oxygen. So in terms of sigma bond, it's electron withdrawing. So inductive, it's an inductive withdrawal group. That's what we say here. However, they donate by resonance. And the resonance donation is strong and it's predominant overriding effect. Okay? These donate by resonance. Now, there's two different ways to show the resonance. We can show it from a neutral molecule. We can also show it from a sigma complex. What I'd like you to do is show resonance structures for both of these. And we'll look at them next time. This would be a sigma complex for a bromination. This is just the starting here. The next, group 2, are going to be weak activators, donators. So they're still activators, but they're not as strong. They're weaker. These are going to be conjugated pi bonds. These are going to have weak resonance donation. Or it can be, and this is probably the most common, alkyl groups. They have inductive donation. So this would illustrate some donation by a conjugated pi bond. And so it adds electron density to the ring. If we consider a sigma complex, the carbocations resonance stabilized, we get additional resonance from the conjugated pi bond. Alkyl groups donate by induction. We know an sp3 carbon is a donating group. We can show that here. The ring attacks I+. We get carbocation. Let's do resonance structures here. Come down. Move up. So these are resonance structures. Somebody tell me why and where does the methyl have an effect? First of all, what type of effect does the methyl have? Donates by induction. We're looking for a stabilizing effect. Where's the stabilizing effect? Information. Versus if the methyl wasn't there. The methyl wasn't there. Where at? Yeah, right here, right? Stabilizes the carbocation by induction. What if the methyl wasn't there? It would just be that, right? If the methyl wasn't there? Which is more stable, that or with the methyl there? Well, this is secondary. With the methyl there, it's what? Tertiary, more stable. That right there illustrates the methyl is an inductive donator. It's going to stabilize your carbocation intermediate. Let's perhaps end on this. Let's go back to the OH group. Let's put this here, this here. Let's put an OH here. What group was OH in? That was my group 1. It's a stronger activator, stronger. That means that this is more stable than that. Why? Because because this group donates by not induction but resonance, and resonance is a stronger effect. Atoms that have a lone pair that are not halogens donate by resonance. Very stabilized intermediate. A methyl doesn't donate by resonance, but it donates by the weaker induction. So this is a weaker effect, but it's still a stabilizing effect. So your alkyl groups are group 2. Next time we'll look at groups 3 and 4. Both of those are going to be deactivators. They're going to be destabilizers. Please look ahead. There is kind of a summary. Look over here. There's some resonance structures that summarize all this. Please look ahead. Be prepared for next time. Remember the seminar today at 1 o'clock, and see you in lab.
You have the